American writer and novelist Pearl S. Buck once said, "If you want to understand today, you have to search yesterday." In this lesson, we're going to graph bivariable data. We will interpret patterns and trends based on data. We will construct a scatter plot. We will find a linear regression equation to a scatter plot. We will determine the linear regression equation. We will find and interpret the correlation coefficient, and we will make predictions based on lines of best fit, all to answer the question, how can past trends predict future occurrences? Let's make sure we're ready for this by taking a look at warm-up number 2. First, we need to graph y is equal to -3 plus 2x. So by having a graph, we come down 3 from the origin and place our first line. From there, we can travel up 2 and to the right 1, given the slope is a 2, and now we have it graphed. Now we need to find the y-intercept of 70 is equal to -2y plus 8. The first thing we're going to do is get this into y is equal to mx plus b form. So we move 2y to the other side, then move 70 to the other side, then divide everything by 2. This lets us see that the slope itself is 4, meaning up 4, right 1, and the y-intercept is -35. Now let's take a look at a problem that you will be able to do at the end of this lesson. Now let's interpret the slope as a rate for Ravi's linear regression equation used from example 5. The equation from that was y is equal to 0.29x minus 22.02. So the slope is 0.29 over 1, which you can also look at as 29 over 100. So for every $100 in increased earning, there is $29 more spent on clothing. Examine this bar graph that depicts how teenagers spend their money. Compare your spending habits with those depicted in the graph. Where are they the same? Where are they different? What about your personal expenses? Are any categories missing from this list? In this lesson, you will learn how to find patterns in data about personal spending. You do this both graphically and algebraically. The data we have been working with in this entire unit has been all simple sets of numbers known as univariable data. For example, when a person keeps a list of weekly expenses, the data in the lists are univariable data. Using univariable data, you can find measures of central tendencies and measures of spread, but sometimes data are collected and presented in pairs. Data represented by pairs of numbers that possibly show a relationship between the paired numbers is called bivariable data. If you keep a list of the days of the month and the amount of disposable money left from your monthly allowance, the set is bivariable data. A scatter plot is a graph that shows bivariable data using points on the graph. Scatter plots may show a general pattern or trend within the data. A trend is a relationship between the two variables. A trend may show a correlation or association between the two variables. A positive correlation exists if the value of one variable increases when the value of the other variable increases. A negative correlation exists if the value of one variable decreases when the value of the other variable increases. A trend may also show a causal relationship, which means one variable caused the change in the other variable. The variable that causes the change in the other variable is called the explanatory variable. The affected variable is the response variable. While a trend may indicate a correlation or causal relationship, it does not have to. If two variables are correlated, it does not mean that one caused the other. We're going to be graphing bivariable data. You can graph a scatter plot by hand or by using graphing software or by using a graphing calculator. Now let's construct a scatter plot. Ravi is a 16-year-old high school student who has a part-time job after school. He is looking to see if there are any trends that relate monthly income to monthly clothing purchases among high school peers. He thinks two variables might relate and want to investigate them using a scatter plot. Below is a list of ordered pairs, that's X's and Y's, where X represents the monthly income and Y represents the monthly clothing expenses for 10 of his classmates. Construct a scatter plot on graph paper by hand, then enter the data into a graphing calculator or use graphing software to create a digital scatter plot. When x is 205, y is 36. The most common error that students make is they do the y-axis before the x-axis. Remember, the order is x's, then y's. Then we have a 242, 45. We do this for all of the points until we have every single point graphed. Let's check our understanding and use that scatter plot. If a student has a monthly income of $250, how much do you predict they may spend on their clothing? To do this, at first, we can roughly draw in a line, but at 250, we see that there is an intersect on the line at what looks like $50. Now, let's interpret patterns and trends based on data. For many people, the cost of contact lenses is a discretionary expense. Jamill buys contact lenses through an online retailer. He has found the type he needs and holds 6 lenses to a box. The retailer has a sliding price based on the number of boxes purchased according to the table on the screen. Examine the scatter plot created using bivariable data in the table where the x value represents the number of boxes and the y value represents the price per lens for the purchase. What do you notice about the number of boxes purchased and the price per lens? Is there an explanatory variable and a response variable? Jamill notices that the higher quantity of boxes ordered, the lower the price per lens charged. Because the y variable decreases as the x variable increases, the correlation is negative. Additionally, the increase in boxes purchased caused the drop in the price per lens. This could have occurred for a number of reasons, such as the retailer being willing to take less of a profit for the increase in sales. Therefore, the boxes sold is the explanatory variable and the price per lens is the response variable. Let's check our understanding of this. The Young Entrepreneurs Club at North Lake High School have been given permission to sell cold water bottles and hot chocolate to students as they walk into school each day as part of the year-long fundraising event. For the entire year, the students kept track of the outside temperature and the sales. 2 scatter plots were graphed, one for each drink, with temperature on the horizontal axis. Which scatter plot do you think showed a positive correlation? And was there causation? Typically, sales of cold beverages will increase as the temperature increases, so the correlation between temperature and cold water sales will be positive. The correlation is probably causal, so temperature is the explanatory variable and cold water bottle sales is the response variable. So how can you predict trends? Well, Tina was looking at the teen spending chart. She noticed that the percentage teens spent on personal care, cosmetics, and accessories is the same as the percentage teens spent on shoes. She decided to poll all the girls in both junior varsity and varsity lacrosse teams at her school. She created a scatter plot on the screen with the school year amount spent on personal care, cosmetics, accessories, and the school year amount spent on shoes as the variables. What conclusion might you draw from this scatter plot? Does it show that the amount spent on personal care, cosmetics, and accessories causes the amount spent on shoes? The scatter plot shows a positive correlation. The increased amount spent on personal care, cosmetics, and accessories does not cause an increase in the amount spent on shoes. Most likely, both amounts increase with student age and student income. Notice the variable of age and income are not mentioned in the problem stated and cannot be classified as explanatory or responsive variables. In this case, age and income would be called lurking variables. A lurking variable is an external variable that may influence how variables are perceived to be related to one another. Because of the unseen lurking variables, people tend to make causality assumptions between variables where they do not exist. Keep in mind that if 2 variables are correlated, they are associated in some way. One does not necessarily have to cause the other. The amount spent on cosmetics does not cause the amount spent on shoes to vary. Let's check your understanding of this and think of an example of a negative correlation for which there is no causal relationship. Now, the answers may vary, and this is just an example. The amount spent on snacks and the amount spent on music downloads. They may be correlated, but the lurking variable for both might be the amount of one's disposable income. This scatter plot shows a relationship between the number of coffee purchases made during a semester and the grade point average for the semester for 10 students. Describe any pattern you see in the data. As the number of coffee purchases increase, the GPA does not increase. So there is no positive correlation. As the number of coffee purchases increase, the GPA did not decrease, so there's no negative correlation. There is no trend in the data, so there is no correlation. Let's check your understanding of this. A high school student collected data on the price of cell phone purchases and the tax for that purchase. The student created a table of ordered pairs for these two amounts and the plan to construct a scatter plot. There should be a positive correlation, a negative correlation, or no correlation. Now, there should be a positive correlation since the tax on a given item is a function of the price of that item. As the cell phone prices increase, the tax for the cell phone will also increase. Let's take a look at some linear regression analysis. Many scatter plot points can be approximated by a single line that best fits the scatter plot. This approximation is made by using linear regression analysis. In linear regression analysis, the equation of the line is found that best fits the points in the scatter plot. This equation may be called a linear regression equation or a line of best fit. The equation is of the form y is equal to mx plus b, where m is the slope and b is the y-intercept. Both m and b are fixed numbers that are needed to graph the line. The linear equation shows a relationship between two variables, usually x and y. In general, one of the variables is the independent variable and the other is the dependent variable. The independent variable can take on any permissible value. It does not depend on the values of any other variables. The independent variable can be considered the input for the equation. The dependent variable is calculated based on the value of the independent variable. It is the output for a given input. The value of the dependent variable directly depends on the value of the independent variable. Both the independent and the variables in the linear equation are used to calculate the slope. The slope is interpreted as the change in y over the change in x. The Greek letter delta is used to represent this change. The formula for the slope is that m is delta y over delta x. The y-intercept, b, is the value on the y-axis where the line crosses the axis. This regression line can be used to display a trend and predict corresponding variables for different situations. It is more efficient to rely on a single line rather than a scatter plot points because the line can be represented by an equation. Recall from your algebra course that the domain is the set of first elements in the ordered pair, and the range is the set of corresponding second elements. Given an x value within the domain, you can predict corresponding y values by interpolation. Given an x value outside the domain, you can predict the corresponding y values by extrapolation. The scatter plot on screen from the beginning of this lesson in which Ravi examined monthly income and clothing expenses. The linear regression equation can be determined for the line that best fits this scatter plot points. The horizontal and vertical labels are indicated to identify the axis, but will not be shown on a calculator display. Generally, the distance the points lie from the line of best fit determines how good a prediction the line is. If most of the points lie close to the line better predicts the trend of the data than if the points lie far from the line. If the points lie far from the line is not good for predicting trends. The correlation coefficient R is a number between -1 and 1 inclusive that is used to judge how closely a line of best fits the data. Negative correlation coefficients show negative correlation, and positive correlation coefficients show positive correlation. If the correlation coefficient is near 0, there is little or no correlation. The correlation coefficient with an absolute value greater than 0.75 are strong correlations. Correlation coefficients with an absolute value less than 0.3 are weak correlations. Any other correlation is a moderate correlation. Now let's determine a linear regression equation. Find the linear regression equation for Ravi's scatter plot from the first example. Round the slope and the y-intercept to the nearest hundredth. The points are given here. Although it is possible to find a linear regression equation using paper and pencil, it is a lengthy process. Using the linear regression feature on a graphing calculator, graphing software, or a spreadsheet produces some more accurate results. Enter the ordered pairs, then use the statistics menu to calculate the linear regression equation. Round the slope and the y-intercept to the nearest hundredth. The equation is y equals 0.29x minus 22.02. Note that graphing programs may differ in the letter they use to represent the slope and the y-intercept. Remember, the coefficient of the independent variable x is the slope. Now, while you can do it on a calculator, there is a way to do this by hand, and the very first thing you would want to do is find the average of x, or x bar. Then you would want to do x bar minus the x variable. Then you would want to find the sum of all of those previous numbers squared. We would also want to find the average of y. So y bar minus those y points would be the next calculation. Then we would want to find the average of the x bar minus the x and multiply that by the average of the y bar minus the y's. Then we would want to do the average of x minus the slope times the average of y. Now, while all of this can be done by hand, it can also be done in a spreadsheet that we'll show here. The first thing we're going to do is go ahead and set up the table with all of the x values. Then in the B13, we will go ahead and average those values. With that average, we're then going to subtract each of the x values. Now we're going to take that average of x value and subtract x squared from it. We will figure out the sum of that column. We'll then fill in all of the y values in the next column, find the average of those y values, then calculate the average minus each y value. Then we will take the average of x and multiply it by an x. That will be multiplied by the average of y minus y for each value. We will find the sum of that column. Then we calculate the slope. We calculate the y-intercept. This will let us find a y, find an x, which will give us the final equation. Now let's check our understanding of this and find the linear regression equation for the scatter plot defined by these points. We can do this on an Excel spreadsheet, and all I really did was duplicate that page and remove its x and y values. So the first thing I did was fill in all of the x values, which went ahead and did calculations for me. Then, filling in the y values, it did all the rest of the calculations and gave me my equation. It is always helpful to keep the resources you build the entire time, because then you can go back to them. Now let's interpret the slope as a rate for Ravi's linear regression equation used from example 5. The equation from that was y is equal to 0.29x minus 22.02. So the slope is 0.29 over 1, which you can also look at as 29 over 100. So for every $100 in increased earning, there is $29 more spent on clothing. Let's check our understanding and see how much of an increase in clothing expenses there is if the income increased by $2. So 29 over 100 is a 29 cents increase per dollar. So $2 will result in 29 cents times 2, or approximately 58 cents more in spending. Let's extend our understanding further. If you use the regression line graph from previously in this lesson that I'll go ahead and put here, determine the monthly income of $200 would approximately correlate with a clothing expense of $59. Would you be interpolation or extrapolation? And explain it. Now, it'll be interpolation, since $200 is within the domain on the graph. Now, let's make predictions based on the line of best fit. Ravi wants to determine an appropriate monthly amount to budget for his own clothing based on the analysis from examples 1 and 5. He works 2 part-time jobs and gets a small allowance from his parents. His total income is $420 a month. What is a reasonable amount for his clothing expenses? The linear regression equation tells Ravi the approximate monthly clothing expense given a specific monthly income. Substitute 420 for x into the equation and compute y, the clothing expense he should budget for. So we're going to get y is $99.78. Based on the data collected, it would be reasonable to assume an expense of about $100 a month. This is an example of Extrapolation, because 420 was not between the low and high x values of the original domain. Let's check our understanding of this and use the equation in example 7, y is 0.29x minus 22.02, to determine the approximate how much of an increase the clothing expense is if the income increases by $2. So there is 29 cents increase per $1. That means that 0.29 times 2 will give us 0.58, which means 58 cents. Now let's find and interpret the correlation coefficient. We are going to determine the correlation coefficient to the nearest 100th for the relationship in Ravi's data from example 7 and interpret this correlation coefficient. This means that R is going to be equal to the number of entries times the sum of xy minus the sum of x times the sum of y. All of this will be divided by the square root of the number of entries times the sum of x squared minus the sum of x squared, and that being multiplied by the number of entries times the sum of y squared minus the sum of y squared. Now you can do this using a graphing device, software, or a website to find the correlation coefficient. But that wouldn't be any fun, so let's use an Excel spreadsheet. The first thing we're going to do once we have it open is we're going to go ahead and fill in all of our x and y values. Then we will find the sum of the x and the y values. We will then multiply all of the x's times all of the y's. Find the sum of that xy column. We will calculate all of the x squared, the sum of all of the x squared, calculate the y squared, the sum of all of the y squared. We'll notice that the number of entries is 10, and then we will calculate the correlation coefficient. So here we can see that the R value is 0.9752. Let's check our understanding and find the correlation coefficient to the nearest thousands for the data in the Check Your Understanding from example 5. Those points were 156 and 245, 420, 330, and 59. So I go to my spreadsheet that I have already copied and pasted a new fresh one onto, and I fill in all of the x values and y values. Then I let the program do the work and do a whole bunch of those calculations for me. It finds the sum, it counts the number of entries, and it computes the correlation coefficient. We get R equals negative 0.98. This represents a strong negative correlation. Now, let's extend your understanding. Carlos did an analysis of two different data sets. One had a correlation coefficient of negative 0.28. The other had a correlation of 0.28. Explain the similarities and the differences between these two R values. Both correlations are weak, since their absolute values are less than 0.3. The first has a weak negative correlation, and the second has a weak positive correlation.